Hello, I'm Mark Hornick with Machine Learning Product Management at Oracle. Welcome. Today we're going to talk about AutoML, hype versus value. For many, automated machine learning, or AutoML, is a shortcut to leveraging AI in support of enterprise business objectives. AutoML automates steps in the machine learning process and helps you leverage your domain expertise and broader data knowledge in combination with powerful machine learning algorithms. And while there's a lot of value to be gained, we need to keep our expectations grounded. Let's start off by asking what you'll get from this session. Well, we start with automated machine learning, what it is and what we can expect from it. What business problems might we solve with AutoML? We'll look at the benefits and how we can take advantage of AutoML. Also, how can we separate the value from the hype? And for this, we need to explore AutoML in the context of the machine learning process. After this presentation, though, I hope you feel excited and more confident about using AutoML to solve your business problems. So let's start with what is machine learning? At one level, it's a type of artificial intelligence that enables predicting outcomes in using large volume data without explicit programming. There are well-defined algorithms that support extracting patterns from data for a variety of use cases and business problems. So then, what's automated machine learning? Well, it's a process for automating aspects of the overall machine learning process. As we'll discuss, many steps in the process can benefit from automation. However, there are still a few that require manual support. So what type of business problems might we address with AutoML? Well, here's just a small sample. Perhaps we want to predict customer credit risk in loan applications, or retain our best customers and address churn, or target customers with the most relevant offers. Perhaps we want to forecast demand or revenue, or maybe take a data-driven approach to predicting when vehicles need maintenance to avoid costly downtime or repairs. But to address getting from business problem to business solution, we need to look at automating this seemingly simple process. We get some data, produce a machine learning model to extract useful patterns from that data to make predictions, and then feed those predictions to applications. But there's a lot more that goes into this process. What's the data we're going to use? How do we produce this machine learning model? How do we make predictions? And more importantly, how do we get those predictions into applications quickly and easily? As we'll see, there's a whole range of considerations, so we'll take this sequence as a high-level cartoon of the ML process. But before we dive deeper, let's talk about AutoML hype. There's likely concern among some, perhaps those studying to become data scientists, that AutoML is going to do away with the need for such skills. Most seasoned data scientists have no concerns, some believing that there's more hype than value there. Others in management may welcome AutoML as a way to address the shortage of skilled data scientists to meet enterprise needs. Is it really the case that AutoML will make data scientists unnecessary? Well, in general, most will agree the answer is no. But there are cases where AutoML can excel. And that leads to the next point. Can just anyone do machine learning with AutoML? While anyone can select a table and identify a column to predict, there's a little more to producing a successful machine learning solution, as we'll see in a moment. However, AutoML certainly helps data-savvy domain experts to derive value from machine learning without data scientist credentials. The third point is that AutoML models are always better than manually produced models. The response to this is, it depends. It depends on the skill of the user to prepare the data and tune algorithm hyperparameters. It depends on the quality of the data and whether a single model is used or perhaps more sophisticated collections of models. So let's peel back the onion a bit to reveal why data scientists will still be needed, but anyone with reasonable understanding of the process can also derive value. And that AutoML-produced models may yield better models faster, but a skilled data scientist may be able to produce superior results. So let's look at the process for machine learning and what we need to understand. What we really need to think about when producing a machine learning-based solution. The first step is business understanding. What are the business objectives and criteria by which we'll measure success? Do we want to increase revenue or increase customer satisfaction? Do we want to understand our customers better or recommend more relevant products? So we need to define the business problem clearly and then see how we might use machine learning to address that problem. Part of this step also involves producing a project plan for the remaining steps of the process. Next, we need to understand what data we have and how useful it is, so hence data understanding. We know that machine learning is fueled by data. What data do we have to work with? One of the benefits of having a database with all your data is that it's easier to access and assess the data that's there. With Oracle, users can reach out to many other data sources transparently through external tables and other methods. With data understanding, we collect data, explore its applicability to the problem at hand, and analyze its quality. Then we come to data preparation, which can involve selecting specific tables, addressing data quality issues like missing values and outliers, joining multiple tables, and creating derived values, also known as feature engineering. For a simple example of a derived value, if we have a date of birth column, we may want to convert this to an age or extract the year and month. Ultimately, we need to produce a table with one record per case and its corresponding target value. That is what we're trying to predict. Take predicting customer churn, which is a classification problem. We want to predict which customers are most likely to take their business elsewhere. So our target column may be a flag indicating customers who've churned a month later to give lead time for us to intervene. Next is the modeling step, where we build the machine learning model using a particular algorithm. In one case, it could be a classification algorithm, like random forest, to address will the customer churn, or does the customer have high, medium, or low lifetime value? Perhaps we have a regression problem to address predicting the credit score of a customer, or house value based on MLS data. We'll take a deeper look at the modeling step in a moment. Now, once you have a model, we need to evaluate it in the context of the business objectives and success criteria defined in the business understanding phase. It's not just a matter of whether the model is accurate, but does it meet the broader business need? And finally, we have deployment, where we may productize the entire process of preparing the data, building the model, and making predictions for use in enterprise applications and dashboards. But deployment also has to do with data and model monitoring and feeding new data back into the process, almost a kind of flywheel effect, reinforcing the solution. Now, in this whole process, where is most of the time being spent? Because clearly, that's where we should focus automation. Well, again, it depends. It depends on many factors, like the problem definition, the available data, quality of the tools, and of course, the skills of the people working on the solution. Some would say most of the time should be spent defining the problem in business understanding, where a well-defined problem is much easier to solve. Indeed, that may shorten the time in the remaining steps, but it's not a guarantee. In other cases, data preparation can take an inordinate amount of time. How do I collect and assemble the data? How do I clean the data? Does it have labels, or is labeling part of the problem? To what extent is feature engineering required, leveraging domain expertise to create new predictors? In others, modeling may be the dominant time sink, where a lot of exploration is required to determine the right mix of predictors, the right algorithm or algorithms, and tuning to optimize model accuracy. So the modeling process itself can take a significant amount of time if you're not able to get the results you need easily, often requiring revisiting previous steps. And then finally, another area where some organizations say they spend the most time is in deployment, because just taking that model and operationalizing it with applications and dashboards can introduce significant challenges, especially where data movement and external or multiple analytical engines are at play. As noted by various industry analysts, many machine learning projects ultimately fail due to issues in the deployment step, whether that's due to scalability, infrastructure complexity, data quality, or other issues. From this, one thing is clear. There's likely no silver bullet. The need for automation exists across a variety of steps. So what can we automate today? I think we can agree that the business understanding step is largely a human activity that doesn't necessarily lend itself to automation. There certainly are use case templates that can help expedite the process and may even be directly applied, but often business objectives and success criteria need to be tailored to the situation. But even with use case templates, someone had to design the machine learning methodology that will ultimately solve the problem. Then there's data understanding, where tools like data catalogs and automated data quality assessments can help with our understanding of data. But this too remains a largely human activity to determine what corrections to data are needed or what data is relevant to a particular solution. Now, data preparation can fall in a couple of areas. One involves aspects that are easy to automate, such as normalizing numeric data or performing one-hot encoding on categorical data for algorithms like neural networks. Such transformations can be automatically applied. In Oracle Machine Learning, which I'll say more about later, we already provide automatic algorithm-specific transformations in the database. In other cases, data preparation really requires the creativity of the data engineer or data scientist to understand how to extract needed values or derive values with domain-specific intelligence. Now, it's easy to automatically extract features from a date column, like year, month, quarter, day of week, and then select those that are most predictive. But suppose I want a more complex combination of variables, perhaps relating humidity, temperature, and vibration. This aspect of data preparation isn't the current realm of automation. Now, the modeling step is one that is most amenable to automation, since the process is relatively well understood, especially for individual models. There's a search space we can specify for selecting algorithms, tuning hyperparameters, and even selecting data used for those specific algorithms. And that process, which we'll talk about more in a moment, can be automated reasonably well. Now, if you're trying to do more sophisticated types of modeling, where you're doing combinations of different algorithms and forming a machine learning pipeline, data scientists typically do this type of modeling themselves. Normally, when we talk about automating the modeling process, it's for an individual model. Now, for evaluation, we're trying to assess if the results we're getting meet the business objectives and success criteria set out under business understanding. I think we'll agree that evaluation is largely a manual process, a very human activity. For deployment, we can get a lot of help through automation. For example, deploying models to an environment where we have scoring REST endpoints, or use SQL queries for making predictions. We can also automate model monitoring, where we set up taking samples and assessing if we have data drift or model drift. And if there's a loss of accuracy, we can rebuild the model. So we see that deployment and monitoring can be largely automated. But consider certain industries like finance or healthcare with regulatory requirements. In many cases, humans are required to review and approve each model before putting it in production, because their predictions may have significant consequences. While one can automatically provide input to human reviewers, the final approval in such situations must be manual. The area of bias and fairness assessment for both data and models may occur in multiple steps. Even with automated bias and fairness reporting, someone likely must decide how to address any issues that are reported. So let's focus our attention on the modeling step as a process that can be significantly automated. We start with a variety of algorithms, and each algorithm has its own applicability and requirements for use. If we have a classification problem, like predicting churn, we might start with a support vector machine. Of course, we expect that our data has been suitably prepared. So then we build our first model. We might use all default settings, or hyperparameters as they're called, for the algorithm. But there are a range of hyperparameters to choose, And as you see here, things like complexity factor, convergence tolerance, number of iterations, what type of solver should we use? There are a lot of options. The combinatorics of trying all of these to produce a given model are really challenging. So we're next going to try to tune the model using these hyperparameters, possibly getting multiple models that will compare and pick the best one for this algorithm. Then we'll go back to the beginning, pick another algorithm, and repeat the same process. So we see the iterative and repetitive nature of the modeling process. We see the complexity to determine which features to use and which hyperparameters to tune, and how. This requires a lot of time, both human and compute, to arrive at the best model. And that's what makes the modeling step a really good candidate for automation. So now let's summarize some of the pain points with traditional machine learning. The demand for intelligent systems is growing exponentially, but there are still insufficient machine learning experts available to analyze all the data and opportunities that arise. As we just showed, each algorithm has its own requirements and hyperparameters, and this can require a deeper understanding to get useful results. Enterprises have rapid model development cycles, where models need to be developed and deployed quickly. And consider a new marketing opportunity, where a model could help identify target customers. If it takes months to get from data to production, the opportunity may disappear. Also, consider fraud detection. A new fraud pattern may appear quickly, and the ability to rebuild, test, and deploy the model equally quickly is essential to limit damages. As such, traditional ML hits enterprises with potentially time-intensive processes and long development cycles. So what can be done about this? Well, there's more to AutoML, where AutoML comes in especially for the modeling step, which we'll focus on going forward. AutoML introduces an efficient machine learning pipeline and eliminates repetitive modeling tasks. But we don't want to do this in a brute force way. Rather, we want to apply some efficient intelligence. For example, perhaps let's apply machine learning to the machine learning process itself to reduce the search space and make finding a better model faster, using fewer compute resources. An AutoML-based solution can help data scientists and non-experts get useful models faster, scaling resources to address more business problems in less time. Further, AutoML can free time that could be spent better on other aspects in the machine learning process, like feature engineering or identifying better or additional data sources. So ultimately then, what is the value of AutoML? We see it as a productivity aid for data scientists. If you're an expert, you can get a preliminary model and understand the settings that AutoML came up with, or the algorithms recommended. And this can be a starting point from which to refine the model. In another case, suppose if our data scientists have a lot of business problems to solve, and they can't spend days or weeks on each one. If they could quickly determine which problems have the greatest chance of success based on the data, and the quality of an AutoML-produced model, they can focus effort to those problems. So it allows triaging projects more efficiently. Another aspect of the value of AutoML is that non-experts can more easily benefit from machine learning, in a sense democratizing it within the enterprise. Users familiar with the basic machine learning process, such as defining the problem and selecting and preparing data, no longer need to understand all the details and requirements of individual algorithms. The AutoML assessment of model quality also guides model selection. And both of these result in our third point, faster time to value. This applies to both experts and non-experts, resulting from the elimination of manual repetition and more intelligent approaches to algorithm and feature selection, as well as model tuning. So, more users can process more data to address more business problems with less effort and less compute. Now, when we talk about using AutoML to solve a business problem, we've said we define the problem and access and prepare the data. And then AutoML for modeling comes in. We can use the API to work with AutoML to select algorithms and features and then tune the model. Alternatively, there are no-code user interfaces that one can use to produce tuned models, so you don't even have to write a line of code. Then, regardless of which path you've taken, you can select the best model, or you can decide to manually refine hyperparameters, or augment the solution with complementary algorithms. When we talk about no-code user interfaces, at least the one I'll be mentioning with Oracle Machine Learning, you can generate code for selected models, which supports code-based deployment. But also it allows you to continue refining the model. When all is said and done, we evaluate models in the context of our success criteria, and then deploy the models in production. But the step that comes after is monitoring and reviewing the solution, which can go back to reassessing the business objectives and success criteria. With that, I'd like to touch on two components that support AutoML in Oracle Machine Learning: OML for Pi and the Oracle Machine Learning AutoML user interface. In OML for Pi, users have programmatic access to functions supporting three key AutoML steps: automated algorithm selection, feature selection, and model tuning. Automated algorithm selection identifies the in-database algorithms most likely to achieve high model quality based on the data, and this is done more efficiently than with exhaustive search. Next is automated feature selection, where the idea is to denoise data and reduce the number of features. We reduce the number of features by determining which are most predictive for the specific algorithm. Now, this is important because when you reduce the number of features, you can not only improve performance, since there are fewer columns of data to process, but you can also improve model accuracy, since there is less noise in the data. And lastly, we have automated model tuning. This is an area that focuses on improving model quality by trying different hyperparameter combinations. Certainly, if you're a novice, this can be a major win, since you don't need to understand those hyperparameters. But even if you're an expert, this may give you a start from which to try doing better. AutoML does the automatic tuning of hyperparameters intelligently, using a gradient descent approach that allows us to zero in on hyperparameters faster, without exhaustive search. Here's a classification example using a popular wine dataset, showing first algorithm selection, where we see the algorithms ranked in order of expected accuracy. SVM with a Gaussian kernel is selected as the best algorithm. Next is feature selection, where we see the features selected as most predictive for that algorithm. And then model tuning, which produces our final tuned SVM model. The other component I'll mention is Oracle Machine Learning AutoML UI, a no-code automated machine learning user interface. Now, by eliminating repetitive and time-consuming tasks, this tool enhances data scientists' productivity as well. And for those who don't write code or don't understand the finer points of the modeling process, it enables non-experts with powerful machine learning algorithms. It accelerates new machine learning projects because you can quickly assess how well a dataset is likely to produce useful results in just a few clicks. From the UI, we can generate editable notebooks for selected models that can be further edited. Perhaps the data scientist wants to see what hyperparameters were used and try to do better, or use this as a starter notebook for a more elaborate solution. Lastly, the AutoML UI makes it easy to deploy in-database models to OML services in just a few clicks. OML services supports real-time scoring from REST endpoints for use in applications and dashboards, along with supporting overall model management. Alternatively, since the AutoML produced models exist in the database, these models can be used immediately for deployment from SQL queries. So let's see a brief demo. This is the OML user interface on Autonomous Database under Quick Actions. We'll click AutoML to see our list of experiments and create a new experiment called wine, using the dataset wine in our user schema. We then select the target we want to predict, in this case, alcohol, making this a regression problem, determined automatically from the target. We can optionally specify other things like the top number of models we'd like tuned, the ADB service level, and even the algorithms we want to try. We see the features with our selected target. And next we can click Start with either faster results or better accuracy. Faster results chooses fewer pipeline combinations to try, while better accuracy explores a broader search space. We see the progress bar with the steps the UI will go through. You'll notice the algorithm selected for this experiment. Let's switch to a completed experiment. This experiment was a classification problem to predict wine cultivators. We see a summary of the experiment settings. Next is the completed taskbar with the steps the AutoML UI performed. We can inspect the individual model results like the confusion matrix and prediction impact ranking for each of the features. We also see the set of predictors used and their algorithm independent importance ranking. Next, we select the model we want to deploy to OML services by specifying the URI, in this case wine, the version of this model, 1, the namespace demo, which allows us to organize our models, and then whether we want to share this model with others. Clicking OK, our model is quickly available for use from OML services via REST endpoints. And just as easily, we can generate an OML for Pi-based notebook that includes the hyperparameters selected for the tuned model. So, in summary, while there is some hype surrounding AutoML that needs to be understood, the value of AutoML as a productivity aid, making machine learning more accessible across the enterprise and to solve business problems faster, should be clear. As automated machine learning continues to evolve, we expect to see more of the overall process to be automated, or at least greater assistance provided across the various machine learning process steps. For more information on Oracle machine learning and to get started using OML, check out these resources. In addition to our webpage and blog, the OML GitHub repository contains code examples and notebooks using the various OML APIs, including the OML for Pi AutoML API. Our office hours provide updates on OML technology, how-tos, use cases, and product demonstrations. To try OML on Autonomous Database, check out the Oracle Live Labs workshops. The link here is for OML Fundamentals, which covers several of the components we've discussed here. So thanks for joining me to learn about AutoML and Oracle Machine Learning. Enjoy the rest of the conference.